like to find the volume of the solid obtained by revolving the area shown here, the area bounded by the curves y equals x cubed and y equals x, and the part in the first quadrant. We're going to revolve this around the y-axis. In this video, I'm going to show you both methods so that you can compare the setups of the two and see how they differ. When we draw our elements, we have two options of how they go, either parallel to the axis of rotation or perpendicular to the axis. The first one we're going to do is perpendicular to the axis. This is going to lead to a disk or a washer. So for each y between 0 and 1, in this case, we have a rectangle of width y. This is, when it's rotated, going to lead to a shape that looks something like this. It's cylindrical, but a very thin cylinder. And it's our washer. So the y values that we're allowing are the y values between 0 and 1. And for each of these y values, we get one of these washers. The dimensions are going to depend on the function. So the width is delta y. The two dimensions we need in order to find the volume of this are going to be this inner radius and the outer radius. The inner radius, or the smaller radius, will come from the distance from the axis of rotation to this function, and the outer radius, or the bigger radius, will come from the distance from the axis to the furthest function. In order to find out what these radii are in terms of y, because we're working with y values, I need to write down the actual equations of the functions. And I'm going to want them in terms of y. So the ones I'm given, y equals x and y equals x cubed, these are not good enough. These will allow me to find the height given x values. And what I want to find is the width, or the distance from the y-axis, given y values. So I resolved these for x in terms of y. And my inner function is x is equal to y, or that distance is y. The outer function is x equals cube root of y, or the distance from the axis to the function is the cube root of y. Once I have these dimensions, I can write down the actual equation that I'm looking for, or the actual volume that I'm looking for. So my volume of this particular washer for this given value of y is going to be pi times the outer radius, or the cube root of y, squared, times delta y, minus pi times the inner radius, y squared, times delta y. If we take all of these now for all the values of y between 0 and 1 and add them up, we end up with an integral that will represent the total volume. It is the integral from 0 to 1, because those are our y values, of pi times y to the 2/3 power minus y squared, all with respect to y. Now we need to compute this integral. And so there's nothing strange going on here. These are just powers of y. So I take my antiderivative, I'll pull out the pi. The antiderivative of y to the 2/3 is y to the 5/3 divided by 5/3, or that's the same as 3/5 y to the 5/3. And then subtract from this the antiderivative of y squared, which is a third y cubed. This will be evaluated between 0 and 1. Evaluating at 0 is nice and easy, so when I plug in 1 raised to any power is 1, I end up with nothing more than pi times 3/5 minus 1/3, which when you combine the fractions, gives you 4 pi over 15. Next, we're going to set it up using cylindrical shells, or using elements that are parallel to the axis of rotation, which remember is the y-axis. So if I draw my elements like this, I'm looking at an element for every value of x, and the values of x that are available to me are x's between 0 and 1. Each of these, when I rotate them, is going to give rise to a shape, and the shape is going to be the shape of a cylindrical shell. It's going to be a hollow cylinder. So forgive the drawing, but it's going to look something like this. And this here is my axis of rotation, or the y-axis in this case. So in order to find the volume, I'm going to need the different dimensions of the different parts. Everything here has to be in terms of x because I'm looking at various values of x giving rise to these cylinders. So I'll need the radius in terms of x, and I'm going to need the height. And the width of the cylinder is, of course, delta x. So first thing, I need the radius. And the radius is just the distance from the axis to where the value actually is. So the axis of rotation being the y-axis means this radius is nothing more than x, the distance from the y-axis to the value of x. So I get a radius of x. My height is going to come from the function itself. And given a value of x, I have functions that represent both the upper part of this rectangle and the lower part. Y equals x for the upper, and y equals x cubed for the lower. And so if I subtract them, that'll tell me the height of my rectangle that I'm moving, x minus x cubed. Now I need to find the volume of this region, and I approximate it by cutting it and creating a rectangular prism that has approximately the same area, the same volume. The little width is delta x. The height here is this height of my cylinder, or x minus x cubed, and the long side is going to be the circumference. So with a radius of x, my circumference is 2 pi times x. So the volume of this rectangular prism, or the approximate volume of my cylinder, is 2 pi x times x minus x cubed times delta x. When I take all my different values of x from 0 to 1 now, add them up, and take the limit, I'll get my total volume in terms of an integral. And it's going to be the integral from 0 to 1 of 2 pi x times x minus x to the third dx. Now to compute the integral, I'm going to pull out the 2 pi and distribute the x, and then just have to take the antiderivative. So I get 2 pi times 1/3 x to the third minus 1/5 x to the fifth between 0 and 1. 0 again gives me nothing, and 1 just gives me the fractions. It's 1/3 minus 1/5, all multiplied by 2 pi. And so I get 4 pi over 15, the same answer as I got before.